Hello everyone, we are Jian Shenyou, Mao Yi, and Zhang Yingning. This is a presentation on our research project. Let's start with a brief introduction about what we've done. We participated in a LibriBrain competition, which provides an extensive dataset for perceived phoneme decoding. To address the challenges we encountered, we conducted an extensive examination to see how results were influenced by different factors. The LibriBrain dataset consists of over 50 hours of MEG recordings of one participant listening to natural English speech. The task is to classify the phonemes in a sample, and each sample has a time window of 500 milliseconds. F1 macro was used as the metrics. The holdout set, which is the testing set for the leaderboard, is already standardized with its own statistics and average groups. As we will show later, these preprocessing steps can heavily degrade the accuracy of our model. During the competition, we faced several challenges. The first one is label imbalance. As you can see, the number of phonemes sample follows a long-tail distribution. This issue can be mitigated using weighted sampling. Secondly, the average grouping approach reduces the size and diversity of training data, which might lead to a drop in performance. Finally, using different means and STDs can also cause problems. MEG are known to have an intrinsic shift between projects and even sessions, and this in particular is what we want to address in our project. We implemented various approaches to tackle the challenges. For data preprocessing, we compared results using different standardization numbers. In addition, to add articulatory information to the model, we mapped each phoneme to a vector denoting phonetic features of the phoneme, as shown in the following table. Next, we optionally repeated the dataset and augmented the data using the listed approaches, each with a probability of 0.3. Finally, for the distribution shift caused by different statistics, we trained a 3-layer fully connected mapper to minimize the MND to align testing features to training distribution. We tried 3 different models shown here. Model A is a one-dimensional convolutional network inspired by ResNet. Model B applies a short-time Fourier transform to get frequency domain information before passing to the CNN network. Model C is similar to Model A, but the core here is changed to a 4-layer transformer encoder. Here are some additional experiments we did. The left-hand side shows the similarity matrix between different trials of their signal means. As you can see, most trials differ with each other by a 0.5 cosine similarity, which is dark red in this graph. The other side is the result of the MMD mapper. The mapper did successfully align the source distribution to the target one. However, it collapses most of the data points into nearly the same position. This may limit the model's ability to preserve feature variations. Finally, here are the results of our experiments. The validation and test dataset actually use the same data, but is standardized with statistics from the training set and statistics from themselves. We can see a significant gap across all models. This shows that different standardization statistics heavily affect the performance of the model. Next, across all dataset splits, CNN plus label balancing outperforms the CNN transformer model, which implies that preprocessing matters more than a complex model architecture. Lastly, let's take a closer look at the last 2 configurations, which use articulatory features and MMD mapper respectively. Compared to plain CNN transformer, articulatory vectors actually cause a performance drop, which might indicate an overfitting to the vector itself rather than a classification task. As for the MMD mapper, the performance drops significantly, which might require further evaluation to identify the cause. In conclusion, we found that MEG signal preprocessing has a substantial impact on performance. This distribution shift between dataset splits is the dominant factor of performance drop. In the future, we will try to implement methods such as per-trial embedding to handle distribution shifts among different trials. That's all for our presentation. Thank you for listening.